Hello everyone. Welcome back to the Joy of Coding at Portland State University. In this class, we use the Java programming platform to learn about topics ranging from test-driven development to object-oriented programming to writing Android applications. There are a lot of things that you can do with Java, and virtually all of those things will leverage the classes, interfaces, and exceptions that are defined as part of the standard Java Application Programming Interface, or API. We're going to begin exploring the Java API with a brief tour of some of the classes available in the java.lang package. These APIs are fundamental to the Java programming language and augment what you've learned about in the Java review slides. So let's dive in. So we're going to talk about some of the standard libraries, some of the standard APIs that augment the Java programming language. Some of these you might have already seen before, and some of them might be new to you. So we'll talk about things like object and system, working with strings, something called the wrapper classes, and also look at a bunch of exceptions. They're all part of the Java Lang package. One of the most important classes in the Java API, if not the most important class, is Java Lang Object. Object is the root class of everything in Java, so all classes descend either directly or through their superclass from Java Lang Object. And because of this, all methods of Java Lang Object are inherited by every other object in Java. So every object has an equals method that compares it to another object. It also has a toString object, which returns a string representation of an object. Now, note that all of these methods have default behaviors which make sense for every object. Specific subclasses may want to override these behaviors to provide additional functionality or different functionality that makes more sense for that object. The toString method is often overridden to provide a string description of a class that makes more sense for it. Hashcode returns, a hashcode for an object so that any object may be used as a key in a hash table. The clone method, which we'll talk about a little bit later, returns a copy of an object. GetClass returns an instance of what's called the object's meta class. This is an object that represents the class of the object itself. It's kind of a mind-blowing concept and one that maybe later in the course we'll get to. Finalize is a method that's called when an object is garbage collected. It's not exactly the same as a destructor, but the whole idea is that it's the opposite of a constructor. So where a constructor will initialize state, if there's any state that needs to be cleaned up when the object is garbage collected, let's say you're reading from a socket or have a connection to a database, the finalize method would be a place to clean that up. And additionally, Java Lang Object provides methods called notify, notify all, and wait, which are used in multi-threaded programs. These are kind of low-level methods for coordinating the work of multiple threads. Another very important class in the Java Programming API is string, Java Lang string. Now, a string is a class, and so you can instantiate that class through a couple of constructors that take different arguments. So you can create a string from a byte array, from a character array, or from another string. And once you have an instance of a string, then you can get information such as the character in that string at a given offset. You can compare that string to another string. You can determine whether or not the string starts or ends with a particular prefix or suffix. You can also use the index_of method to find an occurrence of a character within the string, and the length method to return, the length of a string. As we'll see on the next slide, strings are immutable. Once you create a string, you can't change it. But what you can do is call a method like replace or trim, which will return another instance of string that either has an occurrences of one character replaced with another, or returns a version of that string with the leading and trailing white space removed. So as I said, strings are immutable, and this is actually very important. It allows for some really good optimizations in terms of how strings are represented internally inside the JVM. But very often we need to create textual data. And how do you do that? Well, one way to do that is to use something called a string builder. So this is an object that can be used to create strings out of different pieces of data. Note that string builder is an improvement on the original string buffer class, which you might still see in super old code or maybe get asked about on a job interview. And the whole idea is that string builder performs better in concurrent programs and just has some better implementation than string buffer did. The primary method of string builder is called append, which will append, well, something to a string builder object. And the append method is overloaded to take, well, basically every kind of data that you could throw at it. There's an append method that takes an object. There's an append method that takes an int, double all the primitive types. And this is how you build up a string out of other objects, other data, is by calling the append method. One neat thing about the append method is that it returns the string builder itself. So it allows you to chain together calls of the append method. So you can say something like SB, or refers to a string buffer object. You can say append a string result, and then you can append the number 4 to it. And you can write it just like that. If you need to delete some characters or strings from a string builder, you can do that with the delete char@. method. Similarly, you can insert something into a string buffer at a given offset. You also get the length and a substring within the string builder. And interestingly enough, when you want to convert a string builder back into a string, you just call the toString method, which kind of makes sense, right? Every object inherits a toString method from Java-Lang object, and the implementation of string builder's toString method is to return the string that is represented by that string builder. Now, as you've probably seen, the plus operator in Java is overloaded to concatenate two strings together, or really to concatenate anything with a string. If you look at how the plus operator is implemented, it's actually implemented using string builder. So in your source code, you might write something like system.out.println, the string today's temp is, and then plus temp, where temp is a double. But if you then look at the bytecode that's generated by the compiler, you'll see that what it does is it creates a new string builder object, appends the string today's temp is, appends the double temp, and then prints out the toString value of that string buffer. So string builder is used a lot of places, and something to note is that when you use the concatenation operator, it'll create a new string buffer object, which 95% of the time is fine. But if you're writing some very highly performance sensitive code, or maybe you've got a loop that runs tens of thousands, millions of times, you don't want to necessarily create a new string builder object every time if you can help it. So, there are rare cases where you need to really look at your code to make sure that you understand the impacts of using the plus operator to concatenate strings. And if you decide that the plus operator is not right in that instance, don't worry, you can just use the string builder API directly, which probably means creating your string builder outside of the loop as opposed to creating a new one every time. You'll hear me say this a number of times in the course. Get your code working first and then optimize it. Because, maybe it really isn't that important that usage of the plus operator be replaced by a string builder. Make sure to get it working first, measure the results, and use those results to help you make a data-based decision for what to do next. Java-Lang system is a class that contains, I think of as system-level fields and methods, things about the Java virtual machine and the environment in which it runs. So Java-Lang system has some static fields, which you might have seen already. Right? There's a field called out. So this is system.out, as in system.out.println. And all out is a reference to an object of type printstream. We'll learn about that in a later lecture. That when you write to it, writes to standard out. So system.out.println just invokes a println method on the object referred to by system.out. Similarly, there's a print stream for standard error, and something called an input stream for standard input. There's also a couple of noteworthy static methods on Java-Lang system. There's a method called current time millis, which returns the current time in the number of milliseconds since January 1st, 1970. System.exit will shut down the Java virtual machine and return an exit code, which is an integer, to the host operating system. There are also methods for setting the values of system.out, system.err, and system.in. This is something that you probably don't do that often, but it's something that is possible to do with Java Lang System. The Java Lang Math class is where a number of, well, mathematical and arithmetic methods lie. So if you want to know how you find the absolute value of a number or the square root of a number in Java, this is the class that you use. And these are all static methods that you invoke on the math class. So you've got trigonometric functions, you've got things like exponential arithmetic. You can find the min and max of two numbers and convert between degrees and radians. There's also a random method that will return a random double somewhere between 0.0 and 1.0. Now, there are some APIs in Java that only take objects, and the primitive types like int and long and char are not objects, right? They are primitive types, they are something else. And the primitive types are a nice optimization within the language. I think some people would argue that in hindsight it wasn't that important, but it does allow some very compact storage, and you can work with primitives more easily and with less overhead than you can objects. But what happens if you want to use an int or a double as something like the key to a hash table? The hash table API, which we'll learn about in a different set of slides, only takes objects. Java provides some classes that are called the wrapper classes that essentially represent the primitive types. So you have an object of type integer that can represent the int value of 4 or something. And the fact that there are classes that represent the primitive types give you an opportunity to perform operations and get pieces of information that are unique to that type of data. So for instance, each wrapper class has methods that will convert the particular value that it represents to a different primitive type. So for instance, you might have an instance of capital D double, and if you invoke the int value method, it'll return the little I int for that double. So let's take a tour of some of these wrapper classes. Java Lang Boolean, capital B Boolean, represents, well, a Boolean value, true or false. It has a static method, a class method, called valueOf, which will take a string and parse it as a Boolean value. So if the string is, TRUE, it'll return true. It only has a couple of instance methods. You can convert from the big B Boolean to the little b Boolean by invoking Boolean value. And it overrides equals to compare one Boolean object to another. Java Lang Character provides a lot of information about, well, the character support in Java. And recall that all characters in Java are 16-bit Unicode characters. So there are a bunch of static methods that allow you to do things like, convert between a character, char, and get its int value, so you can figure out, if you want to, exactly what number it corresponds to. Similarly, you can give it a number and return the char value for that digit, or you can figure out whether or not a particular character is a digit or is a letter. And remember, when we're dealing with Unicode, there might be digits and letters that you're not necessarily familiar with. Similarly, you can determine whether or not character is white space. And then there are some instance methods of character that are interesting. You can convert between a capital C character instance and get its char value. And then you can also compare one character to another. And Unicode defines an ordering to the characters, and that's implemented with the compare_to method. As we saw a couple of slides ago, there are wrapper classes for each numeric type in Java, things like int and long and double. And they all descend from a superclass called number. And so number has all the methods for converting between the various numeric types. Since all subclasses of number behave pretty much the same, we'll just look at one of them. And that's Java-Lang integer. So integer has some interesting class methods, static methods. There's integer.parseInt, which will convert a string into an int. Now you can pass it any string. And so if that string doesn't represent a valid integer, the parseInt method will throw a number format exception. And therefore your code can catch the number format exception and handle it appropriately. Java-Lang integer also has a two-binary string static method that will return the binary representation, ones and zeros, of an int, and it'll return it as a string. Similarly, it has a 2-hex string and 2-octal string. There are also two static fields that all the numeric types have that provide the maximum value of the type. In this case, integer.maxValue is the largest int, and the minimum value, the smallest int. And as I said, there are similar classes for all the other numeric types like byte and float and short. Exceptions are a very important part of the Java language and the Java APIs because they convey something that has gone wrong. And when it comes to developing reliable software, you need to be aware of what could go wrong and then recover nicely when something wrong has happened. The class Java-Lang Throwable is the base class for all exceptions. All exceptions descend from throwable. And so all exceptions have methods like getMessage. This will return a string that describes, well, what the throwable object is. Maybe it's usually something along the lines of, here's what's gone wrong to cause this exception. Every throwable allows its stack trace to be printed to some place like standard.error. And a stack trace is basically the description of all of the methods that were executing on the call stack when the exception was thrown. And this is a really powerful tool for debugging. It tells you exactly what code called which other code that ultimately resulted in the exception being thrown. One exception might be caused by another exception, and so then Java-Lang Throwable has a getCause method that will return some other throwable object that caused this exception to be thrown. This allows you to have what are called chained exceptions. And in addition to being able to print the stack trace, you can also get some Java objects that represent the stack trace. That will give you the names of the class, the methods, and maybe the line numbers that were executing when that exception was thrown. Anyone is free to subclass Throwable directly, but there are two subclasses that are built into the API that are worth mentioning. The Java-Lang exception subclass of Throwable represent the kinds of things that a reasonable program may want to catch. We'll see an example on the next slide, but this ranges from like null pointer exception to array index out of bounds to Java I/O exception, all subclass exception. There's another branch of the exception hierarchy, which is another subclass of Java-Lang Throwable, which is Java-Lang Error. And errors are things that are truly not expected. These are things like running out of virtual memory, very serious things, an assertion failed, the kinds of things that you shouldn't expect and really shouldn't recover from. You shouldn't try to recover from an out-of-memory exception. You're kind of hosed at that point. So the Java-Lang package contains a number of exceptions, and here's some of them here. There's some that are sort of inherent to language and language operations, like array index out of bounds exception or class cast exception, which occurs when you have an object and you try to cast it to a type that it is not. So if you tried to cast an integer object to a string, for instance, you don't know how to do that. The integer and string APIs are completely incompatible. You can't call index of a character on an integer, right? It doesn't make sense. Similarly, there are things like null pointer exception, which occurs when you try to invoke a method or reference a field on an object that's null. And number format exception, which we saw before with integer.parseInt, which is thrown when you're trying to parse a string which doesn't represent a valid number. And there are also a couple of errors in the Java-Lang package which are noteworthy. That out-of-memory error, which is thrown when the heap gets full, Or the stack overflow error, when you have too much recursion on your call stack. There's a maximum size of it, and instead of just crashing the virtual machine or getting a seg fault or a blue screen of death or whatever happens these days, the Java virtual machine instead throws a stack overflow error. Your program still crashes pretty hard, but at least your system's okay, and it gives you a pretty decent error message as opposed to just failing. There's a subclass of exception called Java Lang runtime exception. And these are exceptions that are often thrown internally. Null pointer exception and class cast exception, these are both runtime exceptions. A lot of the time, these are the kinds of exceptions that your code can easily test for, right? If you're concerned about an object being null, or if there's a reasonable possibility that it might be null, you can check, see whether or not that object is null before you go call a method on it. As such, these are not the kinds of exceptions that you must catch in your program. You can if you want, but doing something like catching a null pointer exception every time you try to call a method on an object, that would make this code awful, right? That doesn't make any sense. So these are not the kinds of exceptions that you need to declare in your throws clause. Every other subclass of Java Lang exception, however, must be explicitly thrown and then caught. Right? These are the kinds of things that must be declared in the throws clause of a method if the method itself doesn't already handle it. We call these checked exceptions because you must check for them. And so these are things like Java I/O exception. We'll see more about that later, but the whole idea here is that when you perform an I/O operation, something bad might happen, a file might be found, while you're in the middle of reading a socket, the connection gets terminated. These are not, unexpected things, or these things are kind of out of the control of the program. And, as a result, the designers of these APIs want the coders who use the APIs to be aware of it. So they are something that you have to handle or propagate within your code that uses these APIs. For the purpose of this course, when you write exceptions, you should have them subclass exception and not runtime exception. This is to give you practice and experience working with exceptions. It's kind of an academic exercise. In the real world, most often you'll create a runtime exception because exceptions really should be rare. They should be exceptional. But just know that you have the option to use checked exceptions because it can make your APIs easier to read and easier to understand, even though it does put additional burden on the developer who is coding to your API. We saw a little bit of this in the Java Review lecture, but I want to emphasize it again here. We learned about the try-catch block, and just as a reminder, you can catch different kinds of exceptions and handle different kinds of exceptions differently. Here, there's an open file method that you call that might throw a file not found exception. It might also just throw a general kind of I/O exception. And you can handle each one of those differently. Maybe if you get a file not found exception, you just ask the user to put in a new file name. But if you get a more general I/O exception, like there was an error reading from your disk, or a file was truncated, something like that, you probably just want to print out an error message and exit because something clearly is broken. One thing that's interesting to note is that the order of the catch blocks matters. The catch blocks sort of serve as a funnel, if you will, and so then more specific types of exceptions, so basically the subclasses in the hierarchy, need to be mentioned first. Because the JVM will go in order of the declared catch blocks when handling the exception. So in the second example at the bottom of the slide, this won't compile because if an I/O exception, well, a file not found exception is thrown by the open file method, and by the way, file not found exception is a subclass of I/O exception. Because that catch I/O exception block will catch any type of I/O exception, a file not found exception will be handled by that first catch block. Therefore, the second catch block is unreachable code. You'll never be able to execute that code. This is probably not what you had in mind, and so the compiler refuses to compile this, saying, hey, listen, you've got some unreachable code here. Either delete it because you really don't need it after all, or change the order of your catch blocks. This is actually a really nice feature of the Java compiler. You don't want to be writing dead code. It's wasteful and it's confusing because it would give the impression to the reader that, oh yeah, this is what happens when a file not found exception is thrown. It's actually not the case. It'll get handled by that first catch block. There's an assertion facility inside the Java language, and this is activated using the assert keyword. Note that this is a keyword in the language, and this is different from the assertions that you'll see when you're writing unit tests with JUnit or Hamcrest. So this is something that's built into the language, and basically you're saying that you are asserting that some Boolean expression is true. There's an additional syntax. You can say assert some expression and then colon another expression, and that other expression is what's evaluated when the assertion fails and is ultimately delivered to the assertion error exception that is thrown. Now, you use assertions to verify certain facts that you believe to be true about your program. So, for instance, maybe you've just been reading a bunch of bytes from a buffer, and you want to assert that the buffer is empty, that you've got everything. These are usually internal checks that validate the internal logic of your code, not so much, actually, probably never the external logic or really any validation of user input. You can just use regular exceptions for that. Now, because these assertions do incur some expense at runtime, they are off by default. So you can have this in your code, but unless you explicitly enable assertions via the -EA for enable assertions switch to the Java virtual machine, the assertions won't be evaluated at runtime. And because of that, you want to make sure that any code that is evaluated as part of the assertion, anything inside that expression, has no side effects. Because unless the end user runs with -EA, that code will just not be invoked, which might not be what you expect. You may be asking yourself, well, I've got exceptions to propagate errors, I've got assertions to check logic. When should I use each? Again, assertions should be used when you want to verify the internal logic of a method. The kind of little assumptions that we make every day as we write our code. If you've got inputs that come from sort of outside of your code, either directly from the user or maybe you're writing an API yourself and someone's providing you a value in that API, you should use exceptions, something like a legal argument exception, to perform error checking or other validation on that input. And again, using exceptions is probably the right call here. Using an error type is not the right thing because you're not really supposed to catch errors. You can catch exceptions, but not errors. So here is an example of where you can use assertions and exceptions. Let's say you've got a public method which is called setPort, which is called by some other code. You want to make sure that your port is less than or equal to 1024, because I guess you're only running on protected ports here. If it is less than 1024, then you want to throw an exception because you're taking in input from the user, from sort of outside of your code. However, let's say you've got a private method that reads a port from a configuration file, and let's assume the configuration file wasn't tampered with. There, if you trust the data that you're reading, maybe it's been encrypted or something, I don't know. You want to make sure that yes, your port is definitely greater than 1024. And if it's not, then you want to fill with an assertion error that contains the value port. Most of the time, you'll run the assertions enabled only during development and testing. Once the code goes out into the real world, it's less likely that the assertions will provide a lot of value. Here's another example of where you can use assertions to verify program logic. Let's say that you've got a switch statement that switches on the day and you want to return the string. And let's say your day is represented as an int. And so then you can go through your case statement, and if you get to the default and there's an unknown day, then you can just say assert false. Like, wow, I should never get here. Something obviously has gone wrong with my logic because someone added a new day to the calendar. Similarly, if you're using the modulus operator and you're doing mod 3, if your I modulus 3 isn't 0 and isn't 1, then it better be 2. Otherwise, your understanding of the modulus operator changed out from underneath you. The bottom line here is that assertion statements used appropriately and in the right places in the right quantity will make your code a lot better because it verifies the assumptions. And even if you've run it without assertions, anybody reading your code will see what assumptions you've made about the logic of your program. So I want to talk a little bit about how to clone objects in Java. So we learned that there's a clone method on Java Lang object that returns a copy of that object. The copy is meant to have the same state and the same behavior as the object it was cloned from. So, in general, you have an object and you clone it, that cloned object is equal to the original object. However, of course, when you clone an object, you're not going to get the same object. Well, you're making a copy of it. It shouldn't be the same. Even though every object has a clone method, if you try to just invoke it by itself, it'll throw an exception saying clone is not supported. Instead, the way to provide the clone behavior is to implement an interface called clonable and then perform whatever cloning you have to do to make a copy of it. There's a little bit of magic involved here in that if you just implement clonable and you don't override clone, then you'll get what's called a shallow copy of the object. So underneath the covers, JVM will create a new instance of the class. It won't call any constructors though, which is a little weird. And it'll copy the values of the fields. Well, actually, yeah, it'll still refer to the same values. And so this means that even though the initial object is cloned, any objects that it refers to have not been cloned, which may or may not be what you want. If you do want a deep copy of the object, you need to override clone to provide a new implementation. So just as for an example, we have a class called grades, which contains an array of doubles, which are the numeric grades. So here, when we override the clone method, the first thing we do is call super.clone to actually make a copy of it. And then we copy the double array from this grades object to the newly created cloned grades object and return that. You can imagine that as your objects get more and more complex, there's more stuff you have to do inside a clone method. Note here that arrays are clonable, so you can just call the clone method there and it knows how to do the right thing. Now, this discussion of cloning objects brings us to a language feature called covariant returns. And so what covariant returns allow you to do is to have a overriding method, a method that overrides a method from its superclass that returns a subtype of the type returned by its superclass. And this is seen in a number of places, but I think it makes most sense with the clone method. So let's say that I've got a hierarchy of objects that represents animals, and animals are clonable. Animal itself, you can't instantiate just an animal. It has to be a specific type of animal. So it's an abstract class and implements clonable. And just for emphasis, we say that the clone method is abstract. Now, the clone that we inherit from object returns an object itself. It's a plain old object. We don't know what it is. And so that's what we do in animal. However, humans and students apparently can be cloned here, and so the human class extends animal and then overrides the clone method to return a new human, and we change its return type to be human instead of object. And this is legal because a human is an object. So this is an example of a covariant return. Because the clone method of the human class returns a human instead of an object, this is allowed by the language, and as we'll see in the next slide, has some nice benefits. Similarly, for a student, when we clone the student, we override the clone method and change the return type to be student, because student is a subclass of human. Now, why would we want to do this? Well, so this makes it easier to call the clone method. It's a lot less casting, and it's much more explicit about what the clone method is actually returning. Now, covariant returns were a language feature that was introduced to the language several years after the initial release of the language. And in order to provide backwards compatibility, the way it works internally and in the bytecode is a little wonky. In order to retain backward compatibility, if you look at the human class, the bytecode actually returns objects. So if it's called from older code that doesn't have covariant returns, it'll still be okay. However, when you call human.clone, the return type is then automatically, well, not really casted, but it is considered to be human. This is a neat thing. It makes it much easier for the developer when dealing with clone methods or really any place else that you have covariant returns. Do note, however, that if you're introducing covariant returns after the fact, if there's maybe some old code that wasn't using covariant returns, so maybe you've got a professor class which has a clone method that still has object, this won't work because what it's doing is overriding the clone method inherited from human, which now returns human. The professor's clone returns object, and the compiler won't like that because you're not making the return type of the overridden method more specific, you're making it more general. Because object is a superclass of human, not a subclass of human. Another place where you see covariant returns used is in internal versus external classes. So let's say that you've got a class that represents a classroom. You've got a university with a bunch of classrooms. And maybe that is an API that is external that lots of clients are using. Internally, though, you have some implementations. You've got a classroom impl, which implements the classroom interface. You've got a university impl, which implements the university interface. What you can do here is leverage covariant returns and say that get classrooms actually returns an array of classroom impl, and then your internal code can work with the internal type classroom impl and not to cast from classroom to classroom impl all over the place. Covariant returns are an advanced feature of the language, but as you can see, they have some nice benefits at times. So there are a couple key takeaways that I'd like you to get from these slides. Hope you're beginning to see that the Java programming language has a really big suite of classes and exceptions that support the fundamental functions of the language and the platform. So we saw how we could work with text via the string class and the string builder class. We saw the wrapper classes that give you object versions of the primitive types. Talked a bit about exceptions and how there's a class hierarchy that starts with throwable and has several subclasses that provide exceptions that are strongly typed, some of which must be caught and some of which may not be caught. And then we also saw object cloning and covariant return types. So I think this is a good place to stop for right now. There's a lot more that we can learn about when it comes to the standard Java APIs, but I hope that what you learned here gives you a good foundation for getting started with writing real-world Java applications. Thank you for watching, and I encourage you to view more screencasts for the Joy of Coding here at Portland State University.